Hello and welcome back to Homework Help for Math 2. This time we're going to be looking at Unit 8, Circles, Angles, and Shapes, Lesson 4, Madison's Round Garden. In the Ready section, the directions here say find the volume and surface area for each 3D shape. And in this section, we're going to be looking at questions 2 and 3. Question 2 is a cylinder, and question 3 is a rectangular prism. And for both of them, we're going to be looking for both volume and surface area. And starting with volume, when I think about how to find the volume of any prism, not just a rectangular prism, but any prism, as well as how to find the volume of a cylinder, I follow the same general concept. And the same general concept for volume is that what you can do is you can find the area of the base times the height of the figure. All right, that works with any prism. It also works with a cylinder. A cylinder, unofficially a cylinder is a circular prism. The reason why we don't call it that is because a prism needs to have a polygon base and a circle is not a polygon. But it does have some of the same sort of general concepts that a prism does. And when it comes to volume, a cylinder is actually very similar to a prism. So in order to find the volume of any prism or cylinder, all we need to do is we need to find the area of the base and then multiply that by the height of the figure. So with a cylinder specifically, our base is a circle. So what that means is we need the area of the circle. Now, both the top and the bottom are congruent by definition, so it doesn't matter which one we choose. And we can see here that we have a radius of 2. So the area of that circle is going to be pi times 2 squared. All right, that's the area of my circle. And then the height is the distance between the bases. So if you imagine this cylinder sort of standing upright, like a can that's just like sitting normally, the height is the distance between the top and the bottom, which you can see here is 6. So now we're going to take our pi times r squared, and then in order to get the volume, we simply multiply by the height, which in this case is 6. Right. So this is our answer. We just need to clean it up. 2 squared is 4, and 4 times 6 is 24. We're going to leave pi right in there. We're talking about inches, and volume is a 3-dimensional unit of measurement, which means these are cubic inches. So 24 pi inches cubed, or cubic inches. And if I want an approximate answer here, we simply plug in for pi, and we get 75.4 cubic inches. And those are two forms of the same answer for volume. Now, for surface area. With surface area, this is where cylinders and prisms get a little bit different. So surface area is just a little bit more complicated. I'll do this up in green. I'll do this up at the top here. The surface area is the total area on the outside of this cylinder. So if you were to take a cylinder and if you were to sort of like lay it flat, it would look something like this. Okay. So the two circles represent the top and the bottom. And then the rectangle, if you imagine something like a soup can, the rectangle is the label that goes around the can. Okay. Surface area is the sum of all of these areas, of all of the different things in green here. Well, the circles are a little bit easier to understand, so we're going to start with those. So we have two circles, and both of them are congruent, so they have the same area. And the area of any one of the circles is going to be pi times the radius, which is 2, squared. So 2 times pi times 2 squared, that is the area of both circles combined. So now all we need is the rectangle. Now, for the rectangle, the vertical distance here is the same thing as the height of the cylinder. It's 6. Right? So again, if you think of the soup can, it's how tall is the can is going to be the vertical distance of the label, which hopefully makes sense. So all we need now is we need the length of the rectangle. And if you think about what's going to happen, if we sort of take this map, essentially, and if we sort of reassemble the cylinder, what's going to happen is, if we take a look at the top here, the top part of our label is actually going to wrap around the circle. So try to visualize that in your head if you can. The rectangle here, the label piece, is going to wrap perfectly around that circle. Well, that circle, if we're talking about if those are the same distance, that's the circumference, right? So it turns out that in order to get the length of this rectangle, it's the circumference of the circle, so it's simply 2 pi r. And so if I'm going to plug that in now to my problem here, the area of this rectangle is going to be the length, which we just said is 2 times pi times r, in this case is 2. And then to get the area, we multiply by the other dimension, the vertical distance, which is 6. So if we clean this up a little bit, the first term, 2 squared is 4 times another 2 is 8, so that's 8 pi. And then the second term, 2 times 2 is 4, and 4 times 6 is 24. When you're adding terms like this, you can treat the x just like you can treat pi just like you would x. So if you have 8x plus 24x, you get 32x. So if we have 8 pi plus 24 pi, we get 32 pi. Now we're talking about inches. And surface area is a 2-dimensional unit of measurement. So the figure itself is 3 dimensions, but area is always 2 dimensions. So it's 34 pi inches squared. And if we want an approximate answer where we plug in for pi, we end up getting 100.53 square inches. And so that is how we find the volume and surface area of a cylinder. Question 3. The directions are the same as number 2. We want to find both the volume and the surface area, but this time we're dealing with a rectangular prism. Well, like I said for number 2, as far as the volume is concerned, our conceptual understanding doesn't actually change between a cylinder and any prism. In order to find the volume of any prism or cylinder, so our volume is going to be the area of the base, whatever the base happens to be, times the height of my figure, in this case my prism. So if we take a look up at our picture here, my base is a rectangle that has a dimensions of 20 and 12. So if I take 20 times 12, that's going to give me the area of my base. So my area of my base, we said, is going to be 20 times 12. And then the height of my prism is the distance between the bases. It's my third dimension, which is 8, because we're talking about that distance right there. So we're going to take the area of the base, and we're going to multiply by 8. Notice that with a rectangular prism, my volume is relatively easy. It's just length times width times height. I just take one of each dimension and multiply them. But again, conceptually, what we're really doing is we're taking the area of the base and multiplying by the height. So when you do all this multiplication, you get 1920 And we're talking about inches in this problem, and it's volume, so it's cubed. So our final answer here is 1,920 cubic inches. So now surface area. And again, this is where prisms and cylinders diverge a little bit. Get rid of all this. So the general concept of surface area doesn't change. Surface area is the total area on the outside of a figure. With a rectangular prism, you have 6 faces. So we have the bottom and the top. Let's focus on those two first. So let's find the area of those two things. Now, in a rectangular prism, faces that are opposite each other are congruent. So the top and the bottom in this case are identical, which means you have the same area. So we don't have to find it twice. We just need to find it once and then double it. So if we take a look at the base here, the area, just like we found for the volume, the area of the base is going to be 20 times 12, and we have 2 of them. We have the top and we have the bottom. So to account for the red part, our surface area is going to be 2 times 20 times 12. That's the total surface area of the top and the bottom. Now I'll erase that. Now we also have the front and we have the back of this prism. So they're still rectangles, but they're different dimensions. This time, our length is 20, and our other dimension, our height, is 8. So both of those rectangles are 20 by 8. And again, there's 2 of them. So what I'm going to do is I'm going to add, right, because surface area is the sum of all of my areas. We have 2 rectangles that are both 20 by 8. All right, that accounts for the green section here. And then last but not least, the other pair of rectangles that we haven't accounted for yet is on the left and on the right. And you can see here that one of the dimensions is 12, the other dimension is 8. Those 2 rectangles are congruent, so we're just going to find one and double it. So we're going to add 2 rectangles that have dimensions of 12 and 8. So 2 times 20 times 12 plus 2 times 20 times 8 plus 2 times 12 times 8. This is now just pure arithmetic. These are all numbers. We just go ahead and plug in all of this, and what you should get is you should get 990, or not 999, close, 992. Again, we're talking about inches, and surface area is a 2-dimensional unit of measurement, even though the figure itself is 3 dimensions. But area is always 2 dimensions, just like perimeter or circumference is always 1 dimension. So these are our 2 answers for the volume and surface area of this rectangular prism. Now we're looking at the set section. Question 5 says, circle A on the right has a radius of 15 feet as indicated, and a circumference of 30 pi feet, or about 94.25 feet. We could have gotten those ourselves. We didn't need the book to tell us that, because once you know the radius, we can get the circumference and then we can approximate it, but it's nice that we don't have to actually do it. So one less thing for us to do. Segment CD is the diameter of the circle. So as a reminder, the diameter is a special chord of a circle. It has both endpoints on the circle, and because it's the diameter, it goes through the center. It is double the radius, which also means that the radius is half the diameter. Question A, what is the degree measure of arc CBD? So arc CBD is going from there, starting at C, going through B, and then ending at D. Now, this is asking for the degree measure. Notice that this is not the same thing as the length. if you take a look at, if you look a little sneak peek at B, B is asking for the length. A is not a length. A is a degree measurement. And the degree measurement of an arc is equal to the measure of the central angle that intercepts that arc. So whatever that angle is at A, it goes from radius AC to radius AD, and that forms an arc. So whatever the measure of that angle is going to be the same measure, the same degree measure of the arc. Well, because CD is a diameter, it cuts the circle in half. And so an entire circle is 360 degrees, which means in this case, my central angle is going to be half of that. So it's going to be 360. That's a full circle. And because CD is a diameter and it cuts it in half, the central angle is going to be half of 360. And so half of 360 is 180 degrees. That's our answer. Not much more we can do with that. Part B is saying, what is the length of arc CBD? All right, so now we're looking for the length. Let me scroll down so we can see the picture here. Okay. So I want the length of CBD. Well, as we've now seen a few times here, the length of an arc, so CBD, like that. So the length of an arc is going to be some ratio of the entire circumference. The ratio is the measure of the central angle over the full measurement of a circle. So as we've already established, the central angle here is 180, and a full circle contains 360. Now, I want that much of my total circumference around the entire circle. And the circumference of a circle is 2 times pi times r, and in this case we're told that r is 15. If we ignore everything other than the pi here, so we're going to temporarily ignore the pi, 180 over 360 is 1/2. Okay, so that fraction reduces to 1/2. 1/2 times 2 is 1, and 1 times 15 is simply 15. So all of our rational numbers here simplify to 15, and then we still have the pi. And we're talking about feet in this case. So feet, and it's arc length, so it's one-dimensional unit of measurement. And if we want an approximate answer here and we plug in for pi, we end up getting 47.12 feet. So we have both an exact answer and an approximate answer for the length of our arc CBD. Part C says, what is the ratio of the length of arc CBD to the length of the radius? Well, this problem is actually fairly straightforward because it's just asking what happens when we take our answer to B. We'll use our exact answer. So our exact answer was 15 pi. So it's just saying what is the ratio of our answer to B, which we just said is 15 pi. All right, that is the length of arc CBD over the length of the radius. Well, we're told that that's 15. So if we want our ratio, we take our answer to B, we divide by r, so we get 15 pi over 15. Our 15s go away, and so our ratio is just pi. And if you want to approximate pi, a good approximation is 3.14. And because it's a ratio, we don't really have any units here, so we'll just leave it like that. And that is the ratio of our arc length to the length of the radius. All right. Question 6. The circles have a radius of 1, 2, 3, and 4 units respectively. You can also see that that's labeled down here. R equals 1, R equals 2, R equals 3, R equals 4. The diameter divides each circle into 2 equal sectors. Well, we knew that already, but I guess it's nice that they remind us. I guess what they're really doing here is they're saying that the green dotted line is a diameter, which is useful to know. Find the arc length of 1/2 of each of these circles, then fill in the table with the indicated values. All right. So all of our information that we need is already in this picture and or table. Get rid of all our highlighting, I guess. So if we take a look at our table, we've got 4 columns here. First column is just identifying what our radius is, 1, 2, 3, 4. We're not dealing with units here, so all of our values here are not going to have any kind of units like inches or centimeters. They're just going to be like pure numbers. So our radius is 1, 2, 3, 4. And looking at our second column, what we have to do is we have to determine what is the arc length, looking at the smallest circle here. So we're looking for the arc length of BCD. So we're looking for the length of that guy right there. All right. Now, as we've seen really multiple times here, I'll do this, I guess I'll do this on the left. Yeah, I'll do this on the left. So our arc length, well, our description said that the diameter cuts the circle in half. So if I want the arc length for BCD, where BD is my diameter, it means that my arc length is really going to be simply 1/2 of my circumference, because the entire circle is my entire circumference. So the diameter cuts that in half, and so really I just want half of my circumference. So I want 1/2 times, circumference is 2 times pi times r. Now for the small circle, r is 1. So I simply plug that in. And what ends up happening is the 1/2 and the 2 cancels, and then, or rather, it turns into 1, and then 1 times 1 is also 1, and 1 times pi is pi. So this whole thing actually simplifies to simply pi. So my arc length is pi, and that is approximately, as we now know, 3.14. Now, I tend to like to go vertically on these kinds of problems. Not always, but I think it's just going to be easier if we sort of stick with one concept and just do that concept for all four circles, then go to the third column. If you wanted to finish out, the small circle and do the ratio and then the radian measure, that's fine. I just think it's easier if we just go vertically and just bang out all of the arc lengths for these different circles. So my next circle has a radius of 2. So if I want that arc length, so now we're looking for FGH, which is this guy right here, FGH. Again, FH is a diameter, and so therefore it cuts the circle in half, so my arc length is going to be half of my total circumference. And my circumference for this circle is going to be 2 times pi times my radius, which in this case is 2. All right, well, once again, my 1/2 and my 2's cancel, and they get 1. 1 times 2 is 2, and 2 times pi is simply 2 pi. So here, my arc length is 2 pi. And 2 pi, this is an approximation that I would actually encourage you guys, if possible, to memorize. I think most people have a understanding that pi is approximately 3.14. It'll also benefit you if you can have in your head what 2 pi is, just because it's used a lot. So if you can approximate 2 pi very quickly as 6.28, it'll make your life easier down the road. Of course, you can plug it in and sort of get it and all that other stuff. But knowing what 2 pi is approximately off the top of your head can make your life a little bit easier down the road. So something to think about. Continuing on, for the next circle, and we're starting to see a pretty clear pattern here. It's going to be, again, half of our circumference for the same reasons that we talked about before. Circumference is 2 pi times r. Well, now r is 3. The 1/2 and the 2's cancel, leaving me with 3 pi. Now, 3 pi, you don't need to memorize the approximation. I mean, if you want to, knock yourself out, but you don't really have to know it. Turns out that it's 9.42. Memorizing that, I would say, is optional. 2 pi is, I guess, technically optional, but it's recommended. Last but not least, we've got our largest circle. So our circumference over here, we can pretty clearly see what's going to happen. 1/2 times 2 times pi times 4. My half and my 2's cancel, and I'm left with simply 4 pi. Left with 4 pi. And 4 pi, again, you don't need to know this, is approximately 12.56. All right. Now we can move on to our third column here. The third column is asking for a ratio. And specifically, it's looking for the ratio of our arc length. Now, the arc length is the thing that we just found. So in this third column, what we're going to do is we're going to take our answer in the second column, and we're just going to start with that. So the arc length for the small circle, I'll use my exact answer, which was pi. Okay. And then the radius, well, that's the first column. So we're simply going to take our second column and put it over the first column. So our arc length was pi, our radius was 1. Well, anything over 1 is itself, so this is simply pi. And so our arc length over radius is just pi. Next, we have arc length of 2 pi, and our radius was 2. My 2's cancel, and so we are again left with pi. So that is the ratio of our arc length to radius. It's probably not that difficult to see that with the next one, we're going to get 3 pi over 3, which, spoiler alert, is pi. And then for the fourth one, it's going to be 4 pi over 4. And I know this is going to shock all of you, but we end up getting pi again. So every single time, the radius is increasing, the arc length is increasing, but when we take the ratio of those two things, we actually get the same number, and in fact, that number happens to be pi. Very special number in all of mathematics, not just geometry. So our fourth and final column says, what is the radian measure of the central angle? So the radian measure, if we go back up to a picture, I'll look at the big circle here, so the one on the right. So our central angle for the big circle is right here. And I just want to know what is the measure of that angle in radians, not in degrees, but in radians. Well, as we saw in the lesson, we know that this is 180 degrees, and we also know that an entire circle has a radian measure of 2 pi. And so if we want the radian measure of this central angle, which is half of that, our radian measure is going to be simply pi radians. Now, normally radian measures do not have any units associated with them. So if you contrast this with degrees, like 180 degrees has a degree symbol, right? But if you convert that to radians, there's no symbol here normally. Very rarely you may see something like with an R. I think it's a capital R, maybe. But I haven't seen that in a long time. So chances are, if you're talking about an angle and there's no units, especially if it's in terms of pi, that's normally, assuming that it's labeled correctly, that you're going to get a radian measure. So I guess technically we actually did the big circle here. So technically we are down here at our last row. But if we go back to the small circle, notice again that we're talking about our central angle, it's half of a full circle, and so it actually turns out that the radian measure for this central angle is pi. And by a very similar way of thinking, our second circle, the radian measure is again pi. It's half of a full circle, and a full circle is 2 pi. And again, for the third one, our radian measure at the center is pi radians. And that, I believe, is everything with question number 6. Question 7. Question 7 says, why does the arc length increase as the radius increases, but the ratio of arc length to the radius remains the same? So we can type out our answer here. And what I'm going to write here is probably a little bit extra. I don't think you're going to have to write everything that I say here, but as long as at least part of what I write here makes sense, I think you're probably in a good spot. So the reason why this happens is because the distance around the circle, right, which we know that that is basically just circumference, right, and arc length is a piece of the circumference. So the distance around the circle gets longer as the radius increases, which should make sense. As your circle, as the size of your circle increases, the distance around the circle also increases, but the measure of the angle, the central angle, remains the same. Okay? So in other words, both the length and radius are one-dimensional measurements. Okay, they both measure length, essentially, not length times width or length times height. It's just length. So they're both one-dimensional measurements, and so the same scale factor is applied to both as they increase. So if you double the radius, you double the arc length. If you triple the radius, you triple the arc length. By finding the ratio, this scale factor is canceled out, resulting in the original ratio remaining unchanged. So again, I don't think that you need to say all of that necessarily, but as long as you can understand sort of like why our ratio is not changing despite the size of the circle changing, you should be in a good spot. Okay? So that is our answer for number 7. Question number 8. Our directions say each circle has a different radius, so 10, 20, and 30. That's both in the picture and in our table. Fill in the chart / table with the indicated values. So again, we've got small, medium, and large. Radius is 10, 20, 30. I'm noticing that our central angle here doesn't change. So our central angle is going to be 45, 45, 45 every single time. And our second column is asking us to find the arc length. So what that means for our small circle is we're looking for the length of, essentially, of arc EF. So the length of that guy right there. And if I want the length of that, so we'll say the measure of arc EF. Okay. So the measure of arc EF, we can take our circumference, and our circumference is, I'll do this over here on the left, so our circumference is 2 times pi. In this case, our radius is 10, so our circumference is 20 pi. All right. So if I want the arc length, it means we're going to take some ratio of my circumference of 20 pi? Well, because our central angle is 45, what that means is I want 45 over 360. Now this box is kind of small, so I'm going to do the work on the left here because there's not a lot of space to write in the like all this work in the box. So what we want here is we want 45 over 360. Now, if you notice, if you type this into the calculator and you simplify it, you'll get 1/8. And the reason is because 45 is the GCF of both 45 and 360. 45 divided by 45 is 1, and 360 divided by 45 is 8. Also, if you take a look at our picture, it's not that difficult to imagine, if I take a look at the big circle here, it's not that difficult to imagine that if you divide this up like a pizza, you're going to get 8 slices, just like that, right? So seeing that this is 1/8 with 45 degrees, I don't think is that challenging. But again, if you're not sure what 45 over 360 reduces to, it becomes 1/8. So ultimately, what we're looking for here is we're looking for 1/8 of 20 pi. So 1/8 of 20. The 20 goes up into the numerator, and then I can divide out of 4, and I end up getting 5 over 2 pi as my exact answer. And again, there's no units here, so I'm not going to deal with inches and centimeters and all that other stuff. Our exact arc length is 5/2 pi. And if we want an approximate answer here, so if we actually plug in for pi, we get approximately 7.85. Right? And all my sort of scratch work is over there on the left. I think for the next one, I'll try to be a little bit more organized with how I lay this out here. So and again, we're going to go vertically on this problem. So I'm going to finish out the arc length, and then I'm going to go over to my my ratio there. So for the middle triangle, my radius is 20, and we're talking about the measure of arc BC in this case. So BC. And we already know that 45 over 360 is 1/8, so I'm not gonna do that again, right? So what we want here is we want 1/8, because again that's 45 over 360. We want 1/8 of my total circumference, and when my radius is 20, my circumference is 2 times pi times 20. That's my formula for circumference of the entire circle. If I do 1/8, times 2 times 20, I actually get 5. And pi is still there. So my exact answer is 5 pi. And if I approximate this, I get 15.71. So that's my approximate arc length. And then finally, for the large circle, our arc here is JK. So I want the measure of arc JK, just like that. Again, our central angle is 45 degrees. 45 degrees is 1/8 of a circle because a circle is 360, and 45 over 360 reduces to 1/8. So I want 1/8 of my entire circumference, and the circumference of the large circle is, again, 2 times pi times my radius, which in this case is 30. And I'm not going to show all the arithmetic, but if you do 1/8 times 2 times 30, and if you simplify that into a fraction, what you end up getting is 15. You end up getting 15 over 2, and of course we still have the pi in there. But that 15 over 2 comes from 1/8 times 2 times 30. And if we plug in for pi, we get approximately 23.56 as our arc length. Our third column here is asking us to find the ratio of the arc length to the radius. And again, just like with the previous question, all this means is we're going to take our second column and divide by our first column. So for the radius of 10, we found that our arc length was 5 halves pi, and our radius for the first one was 10. So we've got kind of an ugly looking fraction here, but it's really not that bad, because when that 2 in the denominator of the numerator, it's just going to move down to the denominator. So what you end up getting here is you end up getting 5 over 20, and 5 over 20 simplifies to 1 over 4. We don't need the 1 because we have the pi as instead of our placeholder, right? So again, 5 over 2 divided by 10 is 5 over 20, and 5 over 20 is 1/4. So this all simplifies to pi over 4. If that's confusing, if you're not that comfortable with complex fractions, you can always go to the calculator and simply do 5 divided by 2. That's our numerator. And then we're dividing by 10. And when you get, if you convert that to a fraction, there's your 1 over 4. And again, the 1 goes away in this case because our numerator is pi, so we don't need the 1. So our arc length over the radius is pi over 4, which is approximately 0.785. Also, not coincidentally, notice that this is the same as our arc length, except we just moved the decimal place. So 7.85 became 0.785 because we divided by 10. So hopefully that sort of makes sense. For the next row, our arc length was 5 pi, and our radius was 20. All right, this is a little bit easier to see. So now we have 5 over 20, and again, 5 over 20 is 1/4. We don't need the 1 because our pi is going to just stay there. So we're getting pi over 4, which is again approximately 0.785. And then finally, our arc length for our largest circle we found to be 15 over 2 times pi. And our radius was 30. So again, what ends up happening here is the 2 in the numerator of the denominator simply just moves into the denominator. So our denominator becomes 2 times 30, which is 60. And 15 over 60 is again 1/4. We don't need the 1 because the pi makes that redundant. So we end up getting pi over 4, which is still approximately 0.785. Our last column here is asking for the area of the sector. So what we want is the area of these guys, right? The one slice. So in order to find the area of a sector, we need to take some ratio of our total area of All right, and I'm back. So we need to find some ratio of the total area of the circle. So we've now definitely established that 45 over 360 is 1/8. So what we want here is we want 1/8 of our total area. I'm going to start with the small circle all the way on the left. So the area of a circle is pi times r squared. Well, r in this case is 10, so we end up getting 10 squared. So we end up getting 10 squared is 100, so we end up getting 100 over 8 pi, and 100 over 8, our GCF here is 4. So that means that this becomes 25 over 2 pi. So the area of our sector here is 25 over 2 pi. And if we wanted to approximate that, we end up getting 39.27. So approximately 39.27. All right. For the next circle, it's going to be very similar to what we just did, except instead of 10, our radius is going to be 20. So we want, again, 1/8 of the area of the entire circle. If our radius is 20, that's pi times 20 squared. 20 squared is 400, and 400 divided by 8 is simply 50. So no fractions this time. So our exact area is 50 pi. And if we plug in for pi and get an approximate answer, we end up getting approximately 157.08. And if we had units here, all of these would be square units, so it would be inches squared or, centimeters squared, but we don't have units, so we can ignore that. And then for the last one, for our largest circle, our radius is 30 squared. 30 squared is 900, and 900 divided by 8 simplifies to 225 over 2. Because again, there's a common factor of 4, so we factor that out. So we end up getting, for our area of our last sector, the exact area is 225 over 2 pi, which if we plug it in, we end up getting approximately 353.43 square units for the area of that large slice in red in the circle on the right. Moving on to the go section. Directions here say use the diagram for problems 11 through 13. All right. And question 11 says explain why circle F is similar to T, circle T, I guess I should say. Include center of dilation and scale in your explanation. All right, well, this is kind of a interestingly phrased question because we're talking about two circles here, right? Circle F and circle T, and it's basically saying, well, why are they similar? Now, if this little parenthetical, this include center of dilation and scale, if that wasn't there and it just said explain why circle F is similar to circle T, our explanation is extremely simple because all circles are similar to each other. And that would actually be sufficient. So if we didn't have to talk about center of dilation and scale and all that other stuff, and was just saying explain why these two circles are similar, well, all circles are similar to every other circle. It's kind of a pretty, I think, unique property to circles, quasi-unique. So that's all we would need to say without our little parenthetical here. But they want us to talk about dilation and scale. So the center of circle F. So let me go ahead and I'm gonna type in everything, but then I'm gonna have to add in the circle symbol. So I'm gonna leave spaces for the circle symbol. I'm gonna do that at the very end. So the center of circle F, which we know to be point F, can be translated to point T, which is the center of circle T. And again, we're going to add the circle symbol in just a second. The radius, capital T, there you go. The radius of circle F can then be multiplied by a scale factor of 3 to make circle F coincide with circle T. Let me go ahead and add all my circle symbols here before I forget. So I'm going to start at the beginning here. All circles are similar to each other. Now, to talk about dilation and scale, The center of circle F, which is point F, can be translated to point T, which is the center of circle T. So we take F and we simply move it to the right to T. The radius of circle F can then be multiplied by a scale factor of 3. So this radius can get multiplied by 3, resulting in this radius, to make circle F coincide with circle T. So again, super simple explanation is that all circles are similar, but we can also kind of get a little bit into more detail and say that we simply move our center and then dilate our radius, and then we have two circles that coincide with each other. Question 12. If circle T is the preimage and circle F is the image, how would the scale factor be different? So what this means is, instead of going from F to T, what happens if we go from T to F? So what happens if we go in the other direction, right? What happens this time? Well, all that happens is we're going from 6 to 2. Instead of going from 2 to 6, right? If we go from 2 to 6, we multiply by 3. Now, you might be tempted to say, all right, well, you simply divide by 3. And it's not that you're wrong, but scale factor, you almost always want to talk about scale factor in terms of multiplication, right? You don't want to use division when you're talking about, you want to multiply by a scale factor. So instead of saying divide by 3, it's like, what's another way of saying divide by 3 except we want to multiply? Well, if we want to divide by 3, that is the same thing as multiplying by 1/3. So what we can say here for 12 is, get my text box up here so I don't subject you guys to my handwriting, which on the rig is really bad. So the preimage would need to become smaller because the radius would be going from 6 to 2. So the scale factor would be, because again, we have to multiply by something, our scale factor is going to be 1/3. And that is, as soon as I can move this box, there we go. So that is describing what would happen if we went, instead of going from F to T, what would happen to our scale factor if we went from T to F.